Okay, students, I boo-booed a minute ago. I ended instead of pausing, changing, so that's okay. That's okay. I mean, it's just be another video, but you can still watch it. It'll just be a short, real short video. Okay, so you got chapters 10 and 11, one video, and then you got chapter 13, one video. So we won't, the world won't quit spinning maybe. All right, so let's look now. We've got chapter 13. Chapter 13. Sometimes I hate this thing and sometimes I love it. Chapter 13, page, my fingers are so big it's hard to write with it, 474 through 476. So that's pages 474 through 476. So let's look at number 10 to start with. Okay, we got a 35 centimeter tall by 5 centimeter diameter cylinder beaker is filled to the brim with water. What is the downward force of the water on the bottom of the beaker? Okay, so we've got a beaker, okay, got water in it, and the beaker has a height of 35 centimeters, which is equal to 0.35 meters. You got to put it in meters. And it says its diameter, the diameter is what? 5 centimeters, which has a radius, which will, have a diameter of how many meters? 0.05 meters, right? Because it's centimeters is 100 centimeters is 1 meter, so you got to move the decimal 2 places to the left, okay? Okay, so we know we got gravity, 9.8 meters per second squared. We also know the density of water is 1,000 meters cubed. Blast it. Oh boy, I'm sorry y'all. I'll get it right. Kilograms per meters cubed. Okay. We know that's the density of water, and of course that's at 4 degrees Celsius, but we're going to assume all that, all right? What is the downward force of the water on the bottom of the beaker? Okay, well, we know that pressure, you say, well, how in the world are we going to find this? Okay, dang it. Pressure, lowercase p, is equal to the force per unit area, newtons per meter squared, which is equal to 1 PA, right? 1 newton per meter squared is a Pascal, 1 Pascal. So then the downward force is equal to the pressure, not rho, that's rho, pressure times the area, correct? Well, now how in the world are we going to find that? Well, we know that we can find pressure from this, can't we? So pressure would be equal to pressure naught, or the initial pressure, atmospheric pressure, plus the pressure produced by the density of the water, so that's rho times G times what? The distance, right? The height of the beaker. So let's rewrite our equation. So here we go. Wow, okay. So then force is equal to rho, no, not rho, pressure naught, the atmospheric pressure, plus rho of water times gravity times the height of the beaker, the distance, times the area. Lord help. So then force is equal to atmospheric pressure. What is atmospheric pressure? Well, we know atmospheric pressure is 101.3 kilopascals. So it's 101.3 kPa plus the density of water, 1,000 kilograms per meters cubed, times 9.8 meters per second squared, times the height, which is 0.05 meters. And then we got to do the area. Well, now we got to find the radius. So the radius of this would be 2.5 centimeters. Therefore, it would be 0.025 meters. So we've got pi times 0.025 meters squared. Okay? Hopefully everything should be correct. Yes. Okay? Now let's do all that horrific arithmetic. Well, we should come to an answer of approximately 200 newtons. Let's see what it exactly is. Let's double check our calculations here. And I boo-booed. I see a mistake I just now made. I'm sorry. The height of the beaker, the distance or the height of the beaker is 0.35. I bet y'all caught that too, okay? Sorry about that. Let me pause it while I calculate. Don't want to burn up a lot of clock. Okay, and so we get, I forgot to mark my pen. So we get 205.27 or 205.3 newtons. Now let me emphasize something again right here. Probably need to come in here and put a bracket there and a bracket right there. Okay, everybody see that? See what I'm doing? What are you saying, Mr. Shields? All right, when you do the area, this comes out to be 1.96 times 10 to the negative third meters squared. This comes out to be, I think it's 3430, if I'm not mistaken. Yeah, this comes out to be, this calculation right here comes out to be 3430 PA. So you add those two together. When you add those two together, then you multiply it times your area. Okay, so be careful on your calculations there. All right, that's number 10. Now let's look at number 21. All right, so number 21. And number 21 still on the same page, 474. All right, so we got a cargo barge is loaded in a saltwater harbor for a trip up a freshwater river. If the rectangular barge is 3 by 20 and sits 0.8 meters deep in the harbor, how deep will it sit in the freshwater river? Okay, so we got it. It's sitting here in the, this is salt water to start with. And so it comes down here, sits something like that right there, okay? And so it is, all right, let's see how we want to write this. Is low down one trip, rectangular barge is, let's say its length is 20 meters, its width is 3 meters, right? And its height is 0.8 meters, right? Yeah. Let's just say that's this right here. That's not its actual height, but that's this area, this spot right here. Okay, because it's sitting 0.8 meters deep in the water, okay? It's actually higher than that. You know, it's above there. You want it above the water or it'll sink, right? That's just how deep in the water is. All right, now, if you remember buoyancy, remember Archimedes' principle of buoyancy, remember he said that an object in water will displace, or the object's volume, the weight of the water displaced by the object should be equal to, or determined by, I should say, the volume of the water displaced, okay? All right, that's the buoyant force, okay? So let's do the volume of the ocean water that is being displaced. Well, it will be whatever the volume of the vessel is in the water will be how much seawater is being displaced. So we got 20 meters times 3 meters times 0.8 meters, and what does that come to? All right, so we got 60 times 0.08 should be 48. What am I saying? Yeah, 3 times 20. All right, so we got 60 times 0.8, and that gives us 48 meters cubed. So that's how much seawater is being displaced, right? Okay. All right, well then we know by definition of density, we know that the density of water, or the density of anything, is equal to the mass of the water, mass of the seawater, divided by the volume of the seawater. So let's find the mass of the seawater. So the mass of the seawater is equal to the density of the seawater times the volume of the seawater. And so the mass of the seawater is equal to what? Well, the density of seawater, and you have to look this up in your textbook, is 1030, it's a little bit more dense than freshwater, kilograms per meters cubed, times the volume, which is 48 meters cubed. That's a 4, believe it or not. And what do we get? Well, we get 1,000. We get 1,030 times 48. And that comes out to 49,440 kilograms. So that's the volume, that's the mass of the seawater, okay? Well, the mass of the seawater displaced, would it not also equal the volume of the freshwater displaced? Or the mass of the seawater equal the mass of the freshwater? Okay, would it not? Would the masses not be the same? Now the densities are not the same, but look, if it's going to displace 49,440 kilograms of seawater, then y'all, it has to displace 49,440 kilograms of fresh water. Why? Because the volume's not changing. Okay? In other words, the size of the weight of the ship is the same. And we're going somewhere, just hang with me. Okay, the weight of the ship has not changed. Okay, the only thing that's going to change is the density of the fresh water. So, how much fresh water is displaced? You say, will it displace the same volume of fresh water? No. The mass is the same, but the volume is not the same because the density of the fresh water is not the same. So the volume of the fresh water then is equal to the mass of the salt water divided by, because the mass of the salt and the mass of the fresh have to be the same. Okay? Because the size of the ship is the same. The weight of the ship is the same. Okay? Divided by what? The density of the fresh water. Okay? If I don't quit hitting that little button on this marker, y'all, I'm sorry, but my fingers are so big. Okay, so we got 49,400 kilograms divided by 1,000 kilograms per meters cubed, because that's the density of seawater. And so what do we get? Well, we get the volume. It's a little bit different, don't we? It's a little bit higher. Well, it should be because the density is lower. Okay? So we get 49,400 divided by 1,000, and we get what? 49.4, don't we? Meters cubed. That's a 9, believe it or not. I know one thing. I bet y'all be glad when I get through with these videos, especially today. All right, 49.4. Apologize. Okay, so then we know, how do we find, you say, now how in the world are we going to find how deep it goes into the fresh water? Okay, well, it's going to go a little bit deeper. You say, how do you know that? Because the density of fresh water is less than seawater, so it's not going to set up higher in the water. It's going to set lower in the water. Have any of you ever heard about people going to Salt Lake City and they get in the Salt Lake there and they float up higher out of the water? Why? Because the water in Salt Lake is very, very, very salty. It has a much higher density, okay, than plain old fresh water. All right, so how do we find how high? Well, folks, how do we define volume? Volume is what? Length times width times height. And how do we find area? Area is equal to what? Length times width. Well, to find volume, could we say this? Volume is equal to what? And we're going to say height, or D. Okay. All right, could we say then to find volume, could we not say then that it's the area times D or H? Sure we could. So D then is equal to, or height, if you want to call it height, okay, height or distance above the water, is equal to what? The volume divided by the area. Okay. Well, what was the volume of the fresh water? And you say, well, now volume of what? Well, we're talking about the volume of the fresh water. We're talking about the volume of the fresh water because now we want to know how high it sits out of the fresh water. Well, that volume was what? 49.4 meters cubed. The area of the barge is what? Well, the length times the width. So it's 3 meters times what? 2 meters, isn't it? So it's 3 meters times what? 2 meters. 20 meters, excuse me. And so what do we get? So we've got 49.4 divided by 60, and we get 0.82 meters high above the water, or down in the water, excuse me, not above, but down in the water. So notice it sinks a little bit more down into the water, doesn't it? Now, boy, that's a really good problem, because that one really makes you scratch your head and think a little bit, doesn't it? Sure does. That's a really good one. I like that one. All right, so let's move on now. That was number 21. Let's move on to number 37. Okay. All right, so number 37, it says, what does the top pressure gauge in figure 13.37 read? Okay, well, let's draw it first. And by the way, this is on page 475. Okay, so looks like we got a pipe coming in like this, and then it narrows to something like this, and then comes out like that right there. And we've got a gauge right here, and we got a gauge right here. Question mark on that one. This one reads 200 kPa. I'm fixing to scream. So the pressure on that one is 200 kPa. And notice there is oil in this apparatus. And notice that the incoming velocity is 2 meters per second. And the outgoing velocity, if you want to call it V final, is 3 meters per second. So notice that the velocity increases, and the height from here to there is 10 meters. So that's the height, isn't it? It's h, isn't it? Okay. All right. That's 10 meters. Okay. So well, shoot, did I not? Thought I brought the work for that one in. Okay, pause just a minute. God, what am I doing? All right, number 10, number 21. God, dang it, number 37. is A. Testing. All right, here we go. We're back. Hopefully. All right. Okay, so we are looking at Bernoulli's equation in this problem number 37. So Bernoulli's equation dealing with pressure changes from one position to another within a closed pipe. We see then that pressure 2 plus 1/2 rho times the velocity of the water or the fluid, 2, plus the density of the fluid times g times the velocity of the fluid is equal to the pressure 1 plus 1/2 or density velocity squared of the 1 plus rho g y, and that's supposed to be y, my bad, y2, y1. Okay? PGY1. All right? So in other words, Bernoulli says that the pressure, the relationship of pressure from one position in a pipe of flowing, and by the way, this is a flowing liquid, okay, is dependent on its initial pressure and velocity. So it's dependent on what? The final pressure is dependent on its initial pressure and velocity and its final velocity, okay? So that's basically what he's trying to tell us, okay? So what are we trying to get? Well, it says what? What will the top gauge read? So what will this gauge up here read? The top one, top gauge read, okay? Well, basically what we got to do is start plugging everything in, okay? We know V1, we know V2. We know that V1 is what? V1 is 2 meters per second. V2 is 3 meters per second. And so we have an original pressure of what? An original pressure of 200 kPa. We want to find the final pressure, don't we? All right. And the density of the oil, I forgot that, is 900 kilograms per meter cubed. Okay. All right, so what are we looking for? We are looking for P2. So we're solving for this pressure right here. Okay, so let's plug everything in. Now look, we can do some factoring here. If you notice right here and right here and right here and right here, we can do some factoring and we can shift some things around. Okay? So let's see what we can shift around. So P2 is equal to 1/2 rho, and that's the density of the oil, of V1 squared minus V2 squared plus rho times G of Y1 minus Y2. Okay? All right. So we can work that problem just like that right there. And you say, now what'd you do there? Well, look, we've got like terms here and here, and of course the 1/2, and here, the rho and rho G and rho G. I didn't mean to underline the Y2. And then work it like this and solve it for P2. So pressure 2 is equal to 1/2 the density of the oil, which is 900 kilograms per meters cubed, okay? I'm going to do a brackets. V1 squared, well, V1, velocity 1 is 2 meters per second squared minus V2, which is 3 meters per second squared, close the brackets on that, plus the density of the oil, 900 kilograms per meters cubed, times 9.8 meters per second squared, brackets, and we can put a bracket there too if you want to. Y1 is, of course, what? Y1 is at 0, so it actually comes out to be what? 10 meters? It's not going to be a negative answer. It's going to be 10 meters. What's 10 meters? Okay, you don't get negative pressure. All right? All right, now I'm going to pause and we're going to calculate that and then see what y'all get. Whoops. Okay, students. Whoops. Sorry about that. All right, I boo-booed right here. I don't know why I said that wasn't negative, because if you take 0 minus 10, that's a negative 10. There we go. Now everything's adding up. All right, and seems like I've left something off somewhere. Yeah, I sure did. I forgot the P1. My bad. So the equation should be like this right here. There should be a P1 right here. My bad. P1 plus all of that, okay? So then we would have 200 kPa plus all of this right here, okay? Because our final answer, pressure 2, is 109,550. Or we could just say 109.6 kPa or 110 kPa if you wanted to round it up. Because look, that's 200 plus all of this right here. This is negative and that is negative. This value right here I think comes to 2250. This right in here comes to negative 2250. And this value right in here comes to a negative 88,200. And so when you take 200 times 10 to the third minus 2250 minus 88,200, you get 109,550. Okay? All right, I had to clear that up. I knew I kept looking at that equation. I've left something off. Okay? I forgot about adding in the P1. Okay? Right there it is. Okay? All right. Okay, boy, that's a long problem, isn't it? Now let's look at number 43. Last problem. And this is on page 476. Okay, so water flows at 0.25 liters per second through a 10 meter long garden hose. So we got a garden hose and the length is 10 meters, okay? And the flow rate is 0.25 liters per second, okay? And the garden hose has a diameter of 2.5 centimeters, which you know we've got to put in meters, so it's 0.025 meters, and it has a radius of what? 0.0125 meters, if we have to use radius, right? 2.5 centimeters is 0.025 meters. Got to move the decimal 2 places to the left, okay? All right. And the temperature of all of this, the temperature is 20 degrees Celsius. That's important to remember, okay? What is the gauge pressure of the water where it enters the hose, okay? where it enters the hose. That's what we're looking for. All right? So we need to know the pressure where it enters the hose. Okay, now this is Poiseuille's equation. And Poiseuille's equation, and I think it tells you, yeah, if you look in your text or if you go back and look at our video, Poiseuille's equation, I wished I'd have marked it, yeah, is on page 462. It's 13.16. Okay, so basically flow rate, Q, which is equal to the velocity average times the area, is equal to pi, the radius to the fourth power, times the change in pressure, divided by 8 times N. N is the, well, I'm sorry, I told you the wrong thing. Q is viscous flow, and N is, that's actually Nun, is the flow rate times the length of the hose or the pipe. So what are we going to end up solving for this right here? Change in pressure. So change in pressure is equal to what? Well, let's rearrange everything and solve for that. That's 8 nu flow rate times L times Q divided by pi r to the fourth power. So let's plug everything in. So we got 8 times, and what was that value? We have to use the N for the hose, and that is, you have to go to the chart in the text. Forget what page that's on. Yeah, at 20 degrees Celsius for water, it's on page 461. That's the viscosity. I'm sorry, I said flow rate. That's a viscosity. I'm sorry. The viscosity. All right, so we've got what? So let's plug this in. We got 1 times 10 to the what? 10 to the negative third Pascal seconds times the length, which is 10 meters, times Q, which is the flow rate, and that's 2.5. Now, we've got to convert that to meters. We've got to convert this to meters per second, and you got to remember that there's 1,000 liters in 1 meter. So you can divide all that by 1,000, and when you do that, then the value comes out to this right here, 2.5 times 10 to the negative fourth meters cubed per second. Okay? You say, now how'd you do that again? Take this number right here and divide it by 1,000. There are 1,000 liters in 1 meter cubed. Okay, so divide that number by 1,000, and that's how you come to that. Or you could have said 0.25 to the negative third. Either way. Okay, and then we divide that by what? Pi times the radius to the fourth power. And so the delta P, I'm going to write it right here since we've run out of room, should be what? I'm going to pause and let's do some calculations. Okay, so after all that crazy arithmetic, we come to 260.76 pascals of pressure. You could say 261 if you wanted to, okay? So that's using Poiseuille's equation. All right, I hope this helps.